Pass to actually a second and very important topic that is actually also related to what we have spoken until now, that are these requirements of Eurocode 0 related to Annex B. So it is about the reliability differentiation. So actually the Eurocode gives us parameters for almost every actions and also for most of the materials, at least those ones that are mostly used in the, for construction. Anyways, it also provides, as it always do, gives a way to increase or reduce the parameters depending on the situation. So, and actually say, doesn't, also in this case, this annex doesn't give very precise information. Doesn't say you have to do like this. Actually, the suggestion is usually to do using the suggested parameters by Eurocode. Anyways, depending on the actually on your necessity to have a reliability management, maybe in big projects or maybe in complex projects that have different parts that are different, they have to be calculated in different ways, and for each one, so they are related to the probability that the building or the structure collapses because of one or the other one fails. So you can adjust a little bit your parameters, and this is done actually. So something important is that actually fatigue is excluded. So the approach given in this annex recommends actually the following procedures for the management on the structural reliability for construction works. So there are introduces some classes which are based on the consequences actually if the structure fails. So the higher the class is the worse it is if it collapses. So the parameters that are given, usually 1.5 for concrete, is based on the fact that the class of the structure is considered to be the second class. That means is not, so we will see the classes later. So the highest class, and the number 3, is when the structure is very important under the point of view of number of lives and about the economical also impact of a possible failure of the structure. The parameter given are considered as the second one, that is actually a middle way of the importance of the structure. This is actually an annex that tells you if your structure is very, very important, you can increase that. If your structure is like, also if it fails, nobody is going to die, and also is very, very economic, you can reduce these factors. And this is a possibility given to the designer, nothing more. Yeah, so this I was speaking already a little bit about this. Anyways, you find here in relation to the point 2.25 and a procedure to allowing differentiation between various types of construction works in the requirements for quality levels of the design and execution process are given in B4 and B5. If you look at the Eurocode 0, B4 and B5 are these sections of this Annex B, and you can find there all this information. This quality management also control the measures in design. So what actually the Eurocode says is it gives not only the classes of the importance and the reliability classes of the structure, but also says you can adapt a little bit your parameters depending on if the structure is checked by another company and independent person. So if you have this supervisor, and also if you have maintenance more often, and some other parameters that we can see in detail in the next. So something important, this is very important, this is this parameter that allows you to reduce the parameters on actions, but only on 10%. In the end, it's just, it can be from 0.9 to 1.1. I will show later this related to the class. And the reliability index. This reliability index that is beta, you can think about it like you have 10 at the exponent minus something, and this is the probability that your structure fails. So, and this is the exponent. If it is a 3.8, you have 10 high minus 3.8, and this is the probability in maybe 50 years that you have a collapse. So 1 on 10,000 or something like this. For the purpose of reliability differentiation, consequences classes, CC, what I was speaking before, are established by considering the consequences of failure or malfunction of the structure as given in the table. So actually these are kind of important. So these are actually the 3 consequences classes. That means the first one, the higher, the number 3, if you have a very high consequence for loss of human life or economic, okay? Social or environmental consequences, very, very great. For example, grandstands, public buildings. So if you have a stadium where if it collapses suddenly, then a lot of people dies. But it's not what actually is saying here that you have different combinations, because they can be also some kinds of structures that are, for example, masts for high voltage electricity. In that case, nobody, so for example, my region, they are often on the mountains, and if one collapses, nothing happens, nobody dies, but the economical consequences are very high. So in that case, it depends. You can think that it is this, and probably it is, or maybe you can assign to it a lower class because you make your assumption, or maybe play on the number of times that you actually are supervising the object. And then you can apply, for example, lower material parameters because you made an assumption of this type. Of course, these for big projects they must be decided by the designer in accordance with the client. So for CC2, we have a medium consequence of loss of human life, so economic, social, or environmental consequences considerable. Residential and office building, for example, public buildings where consequences of failure are medium. For example, an office building, well, not really medium, whatever. Or low consequence for loss of human life and the economic, social, and environmental consequences. For example, yes, agricultural buildings where people do not normally enter. We will see also an example later on how to compute, for example, a different material parameter in this case. So these also say that actually particular members of the structure may be designed in the same higher or lower consequences class than the entire structure. So you don't have to take the same consequence class for the whole building. You can say the pillars are designed like this because they are very important, but because if one of them fails, the whole structure collapses, but maybe not some walls that you are designing. This is also a possibility. And also what is actually the reliability index. So you see here the effects of actions, the resistance, and what is Z. Z is actually the safety margin. So you can imagine actually that beta is in the normal distribution here of the probability density, that beta is this parameter here, where this is the variance, and this is the average. So here you have the average of Z. Okay, here are also given some values for beta. As I was saying before, actually, you have consequences classes, and you have actually also reliability classes that are one by one with the other. So, for example, here you see actually B index. These, as I told you, these are parameters related to the probability distribution. These that you see here, 1 year reference period, is not the life of the structure. It's just that this parameter was computed for assuming 1 year. Of course, you have a higher variance, and that's why you have also higher beta parameter. So let's assume that we take this as a good one. So the parameters according to Eurocode, this 1.5, 1.15 for steel, or 1.5 for concrete are computed taking 3.8, okay, in the formula. And then with this, you actually get this 1.5 based on the experimental tests they made with concrete or with reinforcement. Yes, for ULS, for fundamental combination for persistent design situation, see, for the same design supervision and execution, a multiplication factor, key F1, we were seeing them before, this 0.9 till 1.8, can be applied to the partial factors. This means that you multiply, so gamma F, that is maybe 1.35 for your persistent action, with 0.9 because it is an agricultural center instead of a very important structure. You are allowed to do this if you want. So also, it is possible to apply partial factors to resistance. This means that you can also use this KF to increase or reduce your resistance of your materials if you think that that this is maybe better for your calculation. But what it says here is that this is not normally used. So usually you put it on actions and not on the resistance of the materials. What otherwise is possible to do for the gamma for the materials is to use it to find out a new parameters with testing. I will show later some small examples that show how to compute that. Assume that you are able to compute the variance of actually and the characteristic value of your material. So you have, of course, to make experimental tests, but they are maybe companies that have some kind of material like for walls building that do that, and then they also provide a material parameter that designers can use in their calculations. Here, I didn't show it maybe yet. These are these KF1 parameters associated to the reliability classes that are also related to the consequence classes. So, and you see, actually, we were speaking about an agricultural building. You can also, so if you think that your structure is not so important in terms of human lives or in terms of economical consequences if it collapses, you are allowed to take 0.9. As well, you are allowed to increase your safety if you think that actually is otherwise very, very important. So you can use, this is maybe something similar to these parameters you saw before, this alpha in this computation of the bridge that actually increased the parameter from 1.5 to 1.67 for bridges, because the bridge was economically very important, and also because, but that one was a different thing, is not related to the reliability, but it functions, it works in the same way. Yeah, here there is also an example. Yeah, accompanying many measures, for example, the level of quality control for the design and execution of the structure may be associated with the classes gamma F. So this is also saying that how much you control your structure during execution is also a parameter that allows you to change your parameters on actions, even if it's not really precise on this point at the Eurocode. Also, there can be cases like masts, as I was saying before. In reasons of economy, the structure might be in RC1, but subject to higher corresponding design supervision and inspection levels. This means that actually you can design it with a low parameter on actions, okay, but then you are forced to make higher supervision. So supervision and maintenance because of economic reasons. Actually, yeah, if a mast of high voltage collapses, so the city doesn't have electricity. So this is bad, and that's why you are forced to do so. Okay, this is design supervision. Differentiation consists of various organizational quality control measures. Yeah, 3 possible design supervision levels. This is actually related to the person that checks the calculation. These are the minimum recommended requirements for checking of calculations, drawings, and specifications. In Italy, you have to apply the first one to practically every new building. So somebody has always to check your calculation, otherwise an external company. Otherwise, you're not allowed to construct anything. So this is something that is maybe exaggerated in Italy, but at least for steel and for concrete, about wood they are discussing about it. Somebody else that in Italy is called the ingegnere collaudatore, as always, to give you a certificate that he checked your calculation, that also checked the building, that also checked that the materials you used, they were conform to the specifications, and then you are able to use the building you constructed. But the Eurocode says that actually relates to each reliability class at different design supervision levels. And so actually, according to Eurocode, you must make this third-party checking just if you are in the highest class, somebody else checking by different person than those originally responsible, and in accordance with the procedure of the organization. This is for second-class buildings. And self-checking, yeah, self-checking, you check by yourself the calculation, but this is not really much. So this is related to this quality management system that also many companies in Europe, also for this certification, ISO 9001, that is really important, especially in Austria. If you want to get projects, this means that you have a system in your company that when you make a drawing, you pass it to another engineer and he controls it, and then he passes it to another one, and at least 3 persons check the projects. Okay. Classification of designers, so this is also not really specific here, and we actually don't really do that in Italy, but I know in Denmark or so, actually there are different kind of civil engineers that are specialized maybe more or less on different structures. And so here it says that maybe also depending on the experience of the designer, you can actually a relevant type of construction work being designed, so you can apply a different reliability differentiation depending on this as well. Or, yeah, alternatively, design supervision differentiation can consist of more refined, detailed assessment of the nature and magnitude of actions. This means, for example, that you can maybe reduce your parameter on wind, if you make tests. So if a university make a very detailed study about the wind force there where you are building your building, you are allowed to reduce the action parameter. Or also, for example, for checking structures, because in some cases, at least for checking a calculation after, you can reduce the material parameters, the partial factors, if you are very detailed information about how much is the load on your bridge, for example, because you measured it in this case. But this is everything depending very much on the project you are approaching. Inspection during execution. Also, 1 second, what time is it? So these are also 3 different classes of inspection, depending on the type of, on how much it is important. And if you have extended inspection from a third-party inspection or normal inspection, so depending, this is also the case for this bridge in Linz. Of course, it is a very important structure. We have, of course, a third-party company that is checking everything. According to Eurocode, if you are, so you can have this supervision on the execution of the same organization that make the design, in case of you are related to the last and the less important reliability class. Okay, and here is also a partial factors for resistant properties. Okay, partial factor for a material or product or a member resistance may be reduced if an inspection class higher than that required according to table B5 or more severe requirements are used. This means that maybe you have a structure that is, you have a reliability class that is 1, but you have an inspection of 3 because of other reasons, maybe depending on the case. In that case, actually you can reduce your partial factors on materials. Let's say that you can take 1.4 instead of 1.5 on the material parameters. This depends, but can be allowed. And so if the Eurocode says you can do like this, so it usually doesn't happen, on my experience, but you are allowed to do that. And you can actually, you have a place in the Eurocode that tells you you can. And it is always good actually to have a standard that gives you some kind of elasticity, that you actually are flexible and you can say, yeah, I designed like this, taking this parameter because the Eurocode tells me that I am allowed to do that. So this is the part that actually is described in this part of the Eurocode. I have here a practical example of how you compute actually a material parameter. So, and actually is given mostly by the reliability index. This is 3.8 or 3.3 or depending on what we compute. Okay, we assume that actually we know the variance of the distribution. We already performed the test and we know actually this parameter Vm, that is the variability here. And you see actually we have to know this parameter here and this parameter here in order to compute gamma m, that is actually, for example, the 1.5 for concrete or 1.15 for steel. So it is assumed that actually the characteristic value is 5%, okay, of the characteristic value. The characteristic part is this part on the left side of the equation. This one is the design part. You divide one by the other and you get something that is greater than 1, of course. So Vm is the coefficient of variation of the material strength, okay? This is, for example, higher for concrete than for steel, because you make 100 tests on steel, and then more or less you get always the same result. You make 100 uniaxial test, compressive test on concrete, and the variance is much higher. So that means that since it is a composite material, so you have a different response in terms of variance of the results. However, so it tells us something important here. So alpha m, this parameter here, no, this way here, can be taken between 0 and 1 according to Eurocode. Maximum importance is 1, of course. So, and beta D is the acceptable reliability index, okay? So this one is actually these parameters that we saw before in the table here, the 3.8. That is usually used by the parameters suggested by the Eurocode. Wait, here. So then, if we use that, okay, we see that what we get for steel, since we have a variance here that it is computed, a variance of VUM, the coefficient of variation, okay, it is 0.08 that corresponds to the common variability of strength of structural steel. Okay, these are parameters that you can only have if you perform the experimental tests, of course. But if you use that, what comes out from the formula is 1.12, and what actually the Eurocode tells you to use is 1.15. This is how it is actually calculated, this value. And here, actually, is the same exactly example, just what changes if I say this is an agricultural building. Then I can reduce this BD, this beta D, because it's not more the reliability class 2, but it's the reliability class 1. So then it is 3.3, and then I can use 1.08 instead of 1.15 or 12 in the calculation of my structure. I'm allowed to do that. Also, if I take the same agricultural building, but is made of concrete and not of structural steel, what changes is actually this VUM, the variability. The variability in this case, so experimentally, is around 0.25. If I use this 1.25 and I put it in the same formula with the same beta D I was using before, the 3.3, then I get 1.28 instead of 1.5. That is what is suggested by the Eurocode. So this is what actually you are allowed to do to reduce your material parameters in the end. Okay, something more I wanted to say about this 4 I's principle. We were speaking about supervision and about inspections and about the third party that is checking your calculation. So this 4 I's principle is related to this and also to many other things. So, and actually, if we want to give a definition, it's just is the requirement that the 2 individuals approve the same action before it can be taken. This is also something that somebody, I remember many years ago, I made an exam at the university in Vienna, and they asked me, so if you want to be sure your calculation is right, what do you have to do? And actually, you cannot compute it again, no? Because if you are sure that what you computed is okay, what can you do? You give it to somebody else to check. So this is the only thing you can do if you want to be safe, and this is the only thing we can do right now, that more people, so many as possible, check the calculation. And also, so these are the main actors that I know actually are active in the construction projects for these operations. It is First, this internal review that is usually called QM management, that is quality management, internal of the company. So usually if you are a big company, you always should be sure that every time you make a calculation, you give it to your partner, you give it to your employee and ask him, check if it is correct, first thing. Second, also for the drawings, of course. So you make the drawings and then you check internally that they are okay. In Italy and in Austria, they check the expert of the ISO 9001 certification that is actually required to get many tenders in Europe, checks these things. So they come and check that you are actually having in your study a sequence of operations, like every time that you have a report, that this report is signed by you, is controlled by another one, and at least a third one. And every one of them, on the first side of the report, they write their name, when they checked, what they found, what they changed, if they changed anything. Then there is the figure of this external design review by auditing engineer, test engineer, or an external third-party company. So this in Italy is very important. So we call it ingegnere collaudatore, but also in Austria it's very important, at least for construction projects. I also worked for a company at the beginning, so where we were actually this proof engineer, we were this external design reviewer. And what we did actually, so the main designer for bridges in these cases sent us the plans, the drawings, and the calculation, and we had to check everything. And then also sometimes this actually was not for all the bridges, but most of them, for the most complicated, we made a new model, an independent model. We put the actions again, everything from new, and we computed the solution. And this was the job I was doing. And then we have construction supervision during execution. And these four important projects is also very important. For example, they are very, very, very strict in this project of the bridge. We are doing the project management right now. They really control independently the direction of the borehole. They come to check all the materials. They also make tests on the anchors after they are installed, and we are going to see some pictures later. Also, actually, this 4 eyes principle is very important in tendering, in giving actually the tender to one company or to another one. So for big construction projects in Italy, in Austria, and Germany, usually you have at least a procurement management team, a legal team, a financial team, a price reasonableness team that actually are people probably also of the first one, the technical evaluation team, a value assessment team, a selection committee, and a design aesthetic team. So many people involved that checks and that give their opinion, that everything actually slows down probably the first design side, but at least in this way you are sure that the design is checked by multiple people in the first phase. So when it is required, a structural design check by an external design reviewer, an engineer. So in Italy, as I was saying before, also during the coffee break, it is practically always needed. So you are not allowed to enter in a building without an independent engineer that gives you a piece of paper with a certificato di collaudo, so checking of the calculation. With that, you give it to the city or to the region, and they allow you to use the building. Otherwise, you're not allowed. I don't know why they are so strict in Italy, because in Austria, for example, they are not so strict. Probably because of the fact that mainly in south of Italy, they tend to construct many buildings in simplified and unchecked way. So they want just to force people to have a certificate by somebody that takes this responsibility. Because as we see later, so in the end, this engineer also shares the responsibility for a possible damage of the building or of the bridge or anything that happens in the structure. Yeah, and the only interventions exempted from this obligation are repair or local intervention. This means that depend on the case, but if you make in your building, you make a small change that doesn't affect the structural stability, you are allowed to don't make this external check. So you can do it just internally. In Austria or in Germany, there is a specification, although in tenders also people, so the client can require to have it or not. For buildings or building classes 4 and 5, this means up to 30 meters. For tanks, bridges, everything, retaining walls or grandstands, this is probably related also to the consequences classes, because grandstands are like structures that, if they fail, have high consequences. Yeah, for other structures, if you do something strange, they say, yeah, then you need an external review. And also, in Germany and in Austria, is the region that decides. So you can put so the different regions that they have in Austria decide on this. And this, as far as I know, is also partial. So in Italy, although yeah, you cannot do much different than this in Italy if you are forced by the Codice degli Appalti to do that on most of it. Okay. Yeah, and also yes, this static test. This is actually what are the responsibility and the requirements of this third-party check. So in Italy, yeah, and also in Austria, so it is an engineer, this reviewer, that must have at least 10 years experience, but not only experience. In Italy, it has to be inscribed to be part of the engineering chamber of engineers. So when you actually start being a professional in Italy, you can join this organization that actually protect your profession as engineer. I will also speak later about this. And actually, you have to join this organization for 10 years. And then you are allowed to make this job, actually, to be the ingegnere collaudatore. And actually, they get, usually get between 0.5 till, I think, till 3% of the amount of the cost for the construction of the structure as a payment. So it's very, very important figure. And also they have a lot of responsibility because, of course, if there is a damage, then they are also involved in that. Yeah, during construction, partial tests must be carried out on the basis of technical difficulties and the complexity of work without prejudice of provisions and specific provisions. So this means this engineer, of course, is involved during the process. So in our case, when at the beginning I was working in that company, I remember once nothing is actually built before the approval of this external reviewer. I remember they were late, and they sent us late these reinforcement drawings. And in this reinforcement drawing, there was an error because the anchoring length was not long enough. They had a mistake, and so actually we called the construction company right away, where they were almost starting to build the foundations. So they always send you the things at the last minute, But in that case, if they really would have built that pile like this and it was not okay, either they would have to recalculate everything and find a way to say that it stands anyways, or they have to demolish what they built until that point. So this was the situation in that case. So the static test, so in some cases is kind of usual. They make also static tests in the meaning of, for a bridge, for example, they pass over the bridge with a very heavy truck, and they measure this. This can happen, not always needed, but what usually make this auditing engineer is actually here contain minimum provisions for the execution of static testing. And must includes actually the checking of the materials as well. So in Italy at least, so the ingegnere collaudatore, this external reviewer, not only check the calculations, not only ensures and visit and supervise actually the building when it is finished that is functional, but also has to certify that all materials used in the construction were certified, that had a CA mark, for example. Yeah, as I was saying before, so the structure may not be put into operation before you have this certificate. I'm not sure how it is in Latvia, I know, but that actually in Italy they tend to be very, very strict on these kind of things. Maybe too strict. In Austria and Germany, they are kind of less strict, but it's also cultural somehow, because in Italy, if you don't control, people tend to make things to somehow not follow the rules. In Austria, somehow, actually, they follow the rules also if you don't tell them, so then they tend to control less. So it's something that actually I experienced many times also on the building site. So also on the building site, Italians' building site can be very, very, very strict under a safety point of view. So you don't come inside easily if you don't have a card, or you have to pass these tunnels. If you are not allowed, it's impossible for you to come on the site. But at least at the first months there in Austria, everybody could come inside on the building site. That is something also difficult to manage sometimes. Yeah, here is also said that at least in Italy, although it's not really well specified, this is related just to reinforced concrete and metal structures, and not for wooden structure. There is a sentence of the court of last year, although, yeah, I don't know. So in some cases, people do it anyways just because they don't want to have problems later. And during construction, when structural elements are installed that can no longer be inspected, checked and tested following the continuation of the construction. Okay, and that is also something important, that at least as I was saying, in these three countries, the checking is not only technical. It's not only technical, but they also check that you had all the authorizations to make their building. So they also check that you had technical requirements to ensure public safety, that they made the necessary tests, that they made, for example, the environmental impact analysis if it was required. So in the end, it has to check many different things, and that's why probably it is also so important. So verification, checking, and the number of samples also. So for concrete, it is also very important. That is performed like specified in the technical standards. Yeah, we have internal Italian kind of strict regulation about how many tests and how many controls on the site and before materials are sent to the sites. And this is also something that the auditing engineer has to examine in the phase of examination. Examination of material test certificates during the checks of steel reinforcement and more generally related to checks of the factory and then production cycle. I had something more about practical examples of checking of the supervision on this bridge here, but I think now it is 1:30, so since this is also related to a project in Austria, and it is also related to various traditions in various countries, then I maybe speak about this later. And if you want now, I'm open for questions about what was discussed until now. If you have any questions about anything, I'm very happy to answer to it.
Hello.
Hello.
Is it working? One small question about the reliability index and the possibility to adjust coefficients for loads and coefficients for materials. Mm-hmm. We can't 100% clearly understand the sentences from the Eurocode. Yeah. Is it allowed to do both for the same project, or is it allowed to adjust either loads or materials?
No, it is allowed to do it. So with this key F index, you can do it either for actions or for resistance. And they say for resistance is not
recommended.
Not recommended. But you can fix both if you do your experimental test yourself. So you can fix then the material parameters by your way, but yeah, this is something that usually nobody do. Yeah.
And another one, just a couple of minutes ago, static testing. What is meant by static testing?
Yeah,
what the tradition?
This is a translation from Italian.
Yeah, but do you really test physically all the structures before covering them?
Yes.
Load them with whatever water or everything?
Yeah, also.
Really?
Yeah.
For all the buildings that are constructed?
No. This is actually something that can decide actually this reviewer. But in some cases for bridges, yes, it's done. Usually it's done. So you load a very heavy truck and you pass over the bridge, you measure the deflection, and you check that it is consistent with the calculations. Or also I have seen it done for buildings, and sometimes they take very big tanks and they fill it with water and they say this is the deflection.
Practically it will probably happen for some specific or strange structures, not for every
No, not for everyone. No. This is an external reviewer must give a certificate is always, but that static testing physically happen, this not. Is actually decision of the reviewer, and of course he try to not do it because otherwise somebody must pay it. Yeah.
And one more thing, the external reviewer participates in reviewing as I understand, the project and the construction stage. It's the same person or the same group of persons responsible for that?
Not always.
What is the distribution of responsibility for that? Because we would find correct that the design is checked by a designer and the construction process is checked by a supervisor?
Might be actually the same person, and sometimes it is, but there are two different things. The supervision during execution is another company. So this external reviewer is, so usually, as it happens normally, is that when the building is finished, this external review go to the site and checks the structure. Usually it works like this, and then it checks these administrative documents and also checks the calculations. This is one person. The other actor that is independent is the supervision on site during construction. And this, for example, there in Linz is an external company that is checking everything. They come there during execution and they control that the construction company does everything properly.
So they do not double down on supervision. They do do an extra supervision. Yeah. Okay, thanks.
Okay.
I have a question.
Question about this external reviewer on the construction phase. If design is changed during construction, does he check once more during construction, or does he check after construction is complete?
Yeah, yes, in this case, actually, when they make relevant changes during the construction, they have to ask both. They have to ask the designer, and also must be allowed by the reviewer if they make a change, a relevant structural change. And also, yes, of course, he controls always the structure as built when it is built. Go there once, but just to make sure that it's clear. So this external reviewer doesn't go every day on the site during construction. Usually, this is go maybe this reviewer came to Linz, I think, 5 times until now. But just because it is a very important region, they were something that was checked. So usually they come when the structure is built, and they check just so that everything was according to the plans and built. They check that this was probably properly executed, let's say.
And say if it is not properly executed, what happens next?
You don't get this certificate of collaudo. That means you cannot use it unless you fix it. So.
Okay, thank you.
Thank you.
Can I have a question here?
Yeah. One last question, please, before the lunch break.
Yeah. About the coefficient of variance. You show the example how to calculate the partial factor if you know the coefficient of variance. Can you share some practical example how designer gets this coefficient of variance? No, because a designer doesn't do testing, but...
yeah, of course. So either you can search in the literature, but usually this is done by material construction companies that actually, for example, they make bricks and then they make testing. Of course, they make 100 tests on their, but it is well specified actually in C and D, in the annex C and D of the Eurocode. Actually, it is also related to the number of tests you execute. So if you make just 5, you of course have a very high beta parameter. If you make 100 or 1,000, since you have a higher number of tests, then you are allowed to reduce this parameter. So it's something that actually engineers get and don't actually compute by themselves. Thank you.
Thank you.
So we discussed about the responsibility and requirements of the auditing engineer, or the engineer that is actually checking the calculations, the administrative things, and also checking the building once it is constructed. Actually, there is a second very important actor in the, let's say, in the monitoring system in construction projects for the 4 Eyes principle. That is actually the construction supervision. The construction supervision in some cases can also be the designer itself, but usually, at least in big projects, it is actually an independent party that is actually identified by the client. So the client, I will show also later, the organization of an example with a project that we have now in Austria. It is an independent company. You have actually the designer. You have the designer that checks what the designer make, and then you have usually the general contractor and some subcontractors for the construction companies, let's say, and you have the construction supervision that checks how it is executed on site. And the client in several states for important projects has also many tasks, many important responsibilities. For example, the construction supervision checks that tests, for example, the materials are made on site, tests that the requirements that are required for the specific project are fulfilled. Like, for example, if you will see later, it is a tender specification in the project to have a specific direction of your pile or your anchor, then they must have usually an independent quality assessment system that checks that this is like this. And they also have, of course, responsibilities because if they don't check, it's not only the construction company responsible, but it's also the construction supervision that is responsible. Everybody shares somehow the responsibility. So the main task of the construction supervision is to assist and supervise the work, giving appropriate instruction when necessary. So actually, usually in big construction company, they give instruction just if you are not doing something as you should do, and this is actually what they usually do. So I will bring the example of this project in Austria. I was speaking already about this. It is a very important structure because also for the city of Linz, it is a very, very important, even just because the first designs for this bridge started in 1920. So they had the idea to make this suspended bridge over the Danube without pylons and just with anchors that are actually anchored to the mountains. And this is something that, as far as I know, was never done before for such a big bridge, because it's a highway bridge with four actually independent highways ways. Yeah. So there is for sure, at least in some pedonal bridge that do like this in Latin America or so, also kind of long, but it was never tried for this in these conditions. And of course, since it is the first time that are doing something like this, nobody is sure it's going to work, and so everybody is checking everything they can check, and nobody wants to take the responsibility, everything for himself, and so there are many designers, there are many controllers, and everybody look at everybody, and everybody put they try to control that things are going are over controlled in order that this bridge is going to work. So as I was saying, is approximately 310 meters long. This is just the length of the bridge, but the cables itself, they are longer, 500 meters or longer, and these are 8 independent cables that are spanned. And I have some pictures now of how it will look when it is finished, and it is actually going to be finished around. So when it continues like this, I think by the end of 2022. And also mounting this structure is going to be very interesting because since it has never been done before, they use some techniques from how is it, a Seilbahn. It is like for gondola, you know, for going to the mountains, actually to span these cables from one side to the other, because of course they also need some kind of machines that can pull down the cables slowly. And also there are problems because you cannot interrupt the flow of the Danube for the boats. So then when they're going to mount the structure, they need actually provisory boats that bring the piece of the bridge, and they are going to give coaction up because they have to deform the bridge in this way. So then when it is charged by that load, it assumes the right deformation. So it is something that they have to do on a provisory boat, and they have such jacks that must push more than 8 tons, and they are high like 2.5 meters. So it's very, very complicated montage as well. So the mounting of the structure is going to be quite complicated as well. But about what we are somehow, I am responsible for, is the making these concrete blocks that are anchored directly in the rock. And as I was telling you before, you don't have much space. Each anchor is like, the borehole is 210 millimeters big, and you have just 70 centimeters from the next one. And so they don't want, first, they don't want that one touches the other one. But second, and it's very important, they need at least at the end of the anchorage, in the zone where the anchorage is stressed, they need at least 1 meter from the next one. Otherwise, they have, they fear that actually the forces in the ground are not well distributed, and either some of the anchors fails, or that all the structure or all the block fails. So it's very important to do things properly. And so I think this is actually the right example for this. Maybe here I also have, I can show a short video, if it works. It's not working. No, maybe I need the internet connection for this, but it was just showing the project itself, because it's not just the bridge, but it's also 2 tunnels that go through the mountains. Because of course, if you see it here, so once so you pass through the tunnel, and then you pass over the bridge, and then you start again inside another tunnel. And then it continues in the city of Linz. And this video, maybe you are able to see it on the slides, or I can give you the link. It is on YouTube. Shows the all projects from the top. Is kind of interesting to see it. Anyways, here I show some pictures. So as you can see, it is a highway bridge, and you can see here that are several independent cables that are separated by some structures here. They stay at a different distance, and then they are anchored, so the bridge itself is sustained with these cables here. So this is going to be, I hope, a very nice structure, and probably they say is going to be one of the symbols of the city of Linz. At this time we are completing the anchorages here, and after we are going to start these here this winter. So there were many, that 110 anchorages on this side, and each one of them can take actually 3,300 kilonewtons. So it is should be sufficient, I think. So these are actually the anchors. There are 11 strands anchors, And as I was telling you before, there is a very small tolerance on the anchorage direction. So this means that they are along 80 meters, and you can have just 80 centimeters. 80 centimeters is so much from the ideal direction. And when you bore, this is, nobody knew how to do that because it's very complicated and there are not many systems that you can make a borehole and actually change the direction or be sure that you get this direction and you continue with that. So, for example, first of all, the surveyor must come and position your machine in such a position that you start perfectly in the right direction with less than 1 degree tolerance, and then you need a machine, actually a device that is placed inside the drilling machine that actually computes where you are. It gives you the position inside the drilling machine, and with that you can see where you are. If you are inside of the tolerance, it's everything okay, and you continue to bore that way. Otherwise, you have to put inside a bend sub, something that allow you to make a curve, and then you actually start drilling in another direction, and then you change the position, and you follow like that. It's something that is made with water drilling, and as far as I know, it was never done or tried before. It was done something similar in the US, still done for actually drilling for oil, because they have to get the oil precisely. But this is another kind of drilling, because in this case you see here this bend sub I was speaking before here. But you have the mud motor here. So in this case, the oil actually strand doesn't actually rotate, because it's only the point here that rotates. But when you drill with water, the whole thing rotates. So you imagine that if this actually rotates, you're not going to make any curve, because it rotates like this, and you have a little bit of eccentricity, but it's going to go straight anyways. So what is done actually is that you rotate with this eccentricity, and at the moment when you want to make a curve, you actually just make it by percussion. So you don't rotate anymore the strand itself, but you just go in this direction by pushing. And in this way you go very slow for some meters, okay? And then you can continue to, once you bend, somehow you can continue to do like that. Nobody knew if this was working, but actually with this technology, you see here, this is put inside, this is called paratrack. It has inside different instruments that can actually measure by means of a magnetic field that you put on the site. Can give you the azimuth, and it can give you the inclination with another instrument that is an inclinometer. In this way, actually, it gives you the position on this angle and the position on this angle, and you are able to know where you are. And these are graphs. For example, you must be inside this tolerance. Okay, this is 1 degree, and this is actually the direction you make when you are drilling. And when you see you're going down, if you're not inside, you have to curve and go up again. Saying like this looks very easy, but it is not, and nobody believes you if you say, yeah, I can do it. You know, you go there and you start making it. Of course, they are going to check. So this is the task of the construction supervision. So they come there with an independent system, and before you put the anchor inside, even though, so they pay more than 4,000 euro every time they come, because they come with a specialized company that comes, check, and then go away. And also they have to stop the constructions, so they also have to pay the construction company because they are not able to work. It's very expensive, but this is what actually do. This is a little bit the organization of the project. This is the client, Asfinag. Asfinag makes actually all the highways in Austria. And then they have, actually this is the test, the control engineer, that the reviewer we were speaking before. So this guy here, he has to check all the calculations. He has to check all materials and say these materials are okay. He has to check the systems that, so the construction company say, okay, we are going to do it like this. It is okay. They ask him, and he, for the client, say yes or no. And all of these people is actually paid by the client. This works for the client, the designer works for the client, and the construction supervision works for the client. The construction supervision, he actually doesn't check the designer, but actually checks the general contractor or the subcontractor. They come on the site every day, and they check that you respect the rules, that you use the materials you have to use. They check that also in Austria is you are not allowed to work on Saturday in the afternoon and not on Sunday the whole day, and you can only work until 8 p.m. and they have very strict rules about this. So they check everything there is to check, also material testing and these kind of things. They supervise also the testing because, of course, they wanted to check properly that these anchors, depending on the soil, it actually lasts. So they performed with these jacks. They made very complicated testing to see actually for tensioning and releasing the anchors to see how much due to friction this system is losing by doing that. And also this has implication also on the structural calculation, because actually they saw here, they saw actually that they had a kind of lost after too many cycles in tensioning the anchors. And so I think now is not us in this case, but the company that is making the structural calculation has to compute to recalculate everything, considering that 5% of this tensioning force is getting lost during so because of friction along the borehole. So this was actually also about quality assessment. So these are common, but there are many more reports that you have to prepare every time you drill a borehole. So you have to give the position every meter while you are drilling, so that actually independently the construction supervision can make a verification and then put the two graphs one on the other, and if it is okay, it is okay. If it is not okay, until now has never been not okay, but in case it would be not okay, they probably would close and ask you to re-drilling. So, and this of course is something that should possibly never happen.